Okay guys, we finally opened our own coffee shop. Congratulations. But I think we have a small problem though. I don't think we're allocating our resources correctly because we're not maximizing our profits and revenues. Do you guys have any ideas about that?
Yeah, well, I actually looked at our resources and I saw that we're using our milk and coffee beans wrong. We're putting in different amounts that are not maximizing our profits.
Oh, I think there's a mathematical way to solve this problem.
Yeah, actually, we can look at partial derivatives and optimization involving coffee beans and milk.
Welcome to our exploration of the intersection between calculus and coffee. Since our coffee shop is new, we have to put an emphasis on optimization and profitability of each of our cups of coffee. Today, we're diving into how advanced mathematics isn't just for the classrooms or theoretical concepts. It's brewing in every single one of our cups of coffee served in this coffee shop. Imagine every choice made in the ingredients of your favorite coffee. How much milk to add, how many grams of coffee beans are used, can be optimized for maximum flavor and profitability. That's where calculus comes in. Today, we're specifically looking at how partial derivatives and optimization play crucial roles in decision making. These tools from calculus help coffee shop owners like us determine the exact amount of each ingredient needed to perfect a recipe while maximizing economic efficiency. Our project uses these mathematical concepts to formulate a profit function that considers the cost of coffee beans and milk. We'll show you how altering these variables slightly could lead to a more profitable operation, ensuring that every cup of coffee not only tastes good, but also contributes positively to the shop's bottom line. Next up, we will show you how we blend calculus with coffee, demonstrating the practical utility of mathematics and optimizing everyday operations, and also ensuring that every sip is as profitable as it is delicious. So let's get on with the math and discover the perfect brew.
Alright, so we have already introduced our company and our business model. But we have a problem. We are not able to maximize our revenues. Talking with our research and development team, they think that it's because under our budget constraint, we are not able to allocate our resources efficiently. So let's take a look on how we can solve these issues.
Now, as my colleague Jorge mentioned, we have a small problem in terms of maximizing our revenue. However, I believe there is a small fix for this. The dynamic world of business, understanding how small changes can have big impacts on operations is crucial. This is where partial derivatives come into play. A partial derivative measures how a function like total revenue or cost, for instance in our coffee shop, responds to changes in one small variable. In this case, coffee in kilograms and milk in liters, while keeping the other one constant. It's a powerful tool for analyzing the effects of adjusting factors such as pricing or production levels individually. Now, let's talk about optimization problems. These are challenges where we aim to find the best outcomes. In our instance, we try our best to find the maximization of our revenues under the given constraints. By applying partial derivatives, we can pinpoint the exact levels at which our revenue is maximized, ensuring that decisions are not just good, but also really optimal. Firstly, before moving to revenue maximization, let's see what we are working with. In our instance, X represents the coffee in kilograms and Y represents the milk in liters. Our total budget constraint is $64 per day. Our cost for coffee is $4 and our cost for milk is $8. According to this information, our budget constraint comes around at 4x plus 8y equals 64. And finally, 30x minus 2x squared plus 50y minus 3y squared is our total revenue function. Before we move forward, we have to come up with a Lagrangian function. In this instance, we join our total revenue function and our budget constraint, and we get our Lagrangian function, which equals to 30x minus 2x squared plus 50y minus 3y squared plus lambda, open parentheses, 4x plus 8y minus 64, close parentheses. With this, we can find our critical points and maximize our revenue. How this works, firstly, we had to find our first derivatives and equate all of them to 0. Now, our first step is to figure one of the variables, in this instance lambda. To do this, we have to look at equation 1 and calculate lambda. Lambda equals 30 minus 4x divided by 4. Now, our step 2 is to substitute lambda from equation 1 into equation 2. Our equation 2 is 50 minus 6y plus 8 lambda equals 0. Now, our equation will look like, after substitution, 50 minus 6y plus 8, open parentheses, 4x minus 30 over 4, close parentheses, equal to 0. Now we have to open the parentheses, and we're going to have 50 minus 6y plus 2, open parentheses, 4x minus 30, close parentheses, equals to 0. And finally, our final equation will look like as 8x minus 6y equals 10. Now, the third step is to simplify the budget constraint, which is 4x plus 8y equals 64. After simplification, which is just dividing the whole function by 2, it is going to be 2x plus 4y equals 32. Now, in step 4, we just write down the given equations, which is 8x minus 6y equals 10 and 2x plus 4y equals 32. Our step 5 includes just eliminating the x from a single equation. How we do this is we multiply the second equation by 4 and we subtract it from the first one. After the multiplication, our equation is going to look like as 8x minus 6y equals 10, and we're going to subtract 8x plus 16y equals 128. Step 6 is to simply just solve the final equation. Our final equation just looks like 22y equals 118. Now let's find y. If we want to find y, we have to divide both sides by 22, which is going to give us y equals 118 divided by 22, and y equals 5.36. Now, step 7 includes just doing every single step, but for x. We have our original functions, which are 8x minus 6y equals 10 and 2x plus 4y equals 32. Now, let's isolate y from second equation, which is 4y equals 32 minus 2x, which is simplified to 8 minus 0.5x. Now, for step 9, we just have to substitute the given equation of y into first equation, which is 8x minus 6, open parentheses, 8 minus 0.5x, close parentheses, equals to 10. Now let's simplify. This is going to be simplified as 8x minus 48 plus 3x equals 10. Now we have to move x's to the left side and full numbers to the right side. This is going to give us 11x equals 58. And to find x, we just have to divide both sides by 11, which is going to give us x equals to 58 divided by 11. And our final answer for x is 5.27. Now, we got the answers, but what does this really mean? Well, x, which means coffee in kilograms, equals to 5.27. Which means we should use 5.27 kilograms of coffee to maximize our revenue. Same goes for y, which means milk in liters. It equals to 5.36, which means we should use 5.36 liters of milk to maximize our revenue. Now we know the numbers, we just plug them into our total revenue function and we get the maximization of total revenue, which equals to 284.365.
And as we all can see, derivatives and math can be extremely useful to solve problems on our daily lives and business-related tasks. Thank you for your attention.